Hello, this is a video about collisions and how to solve problems involving them. So, the most important tool you use to solve problems involving collisions is called the conservation of momentum, which is this. The combined momentum at the beginning, before the collision takes place, is the same as the combined momentum after the collision takes place. When I say combined momentum, I mean the momentum of every object involved in the collision. So let's say that you have two cars. You have a red car that's moving this way, then you also have a blue car that's moving this way. After they collide, they're moving in different directions. They bounce off each other, and you want to know what happens. Well, the way you figure that out is you say before the collision, the momentum of the red car plus the momentum of the blue car before they hit, so the initial momentum of the red car and the initial momentum of the blue car is going to equal the final momentum of the red car. So the final momentum of the red car and the final momentum of the blue car added together. So final. So after they hit, they are obviously not going to be going in the same direction. This red car is going to be bouncing in the opposite way, right? The red car is going to be going this way, and the blue car is maybe going to be going this way. And the momentum that they have has been redistributed, but the total amount is the same before and after. So this is how you solve it. Combined initial momentum is the momentum of every object. If you have three objects colliding, you would have three of these. If you had four, you would have four, and so on. Notice that momentum, this P right here, is the same as the mass times the velocity. So wherever you see this P, you can replace it with this, the mass times velocity. So what this means is that in our collision of a car, where you have a red car going this way, then you have a blue car going this way, and you want to know what's going to happen after, you take the momentum of the red car, and momentum is the same as mass times velocity. So you add to that the momentum of the blue car before the collision. So I'm going to say initial. That is going to equal the same number as the combined momentum at the end. And I'm using different colors to tell you that this mass is not the same as this mass. They're different cars, so they have different masses. This is the equation that we will use to solve collisions with two objects. You have two on the left and two on the right. This works all the time. So here's an example. A baseball with a mass of 1 kilogram is thrown to a batter at negative 20 meters per second. It's negative because it's going towards the batter. The batter swings an 8 kilogram bat at 25 meters per second forwards. That's what this plus means. After the hit, the bat's velocity is positive 4 meters per second. What's the new velocity of the ball? So this is a collision involving two objects. We have a ball and a bat at the beginning. We have a ball and a bat at the end. So I'm just going to take this equation and put it at the bottom here, and then we can start plugging things in. So I've hopefully made this a little clearer. The mass of the ball at the beginning times the velocity of the ball at the beginning, plus the mass of the bat at the beginning plus the velocity of the bat at the beginning is equal to the mass of the ball at the end times the velocity of the ball at the end. The F means final, plus the mass of the bat and velocity of the bat at the end. And notice that this mass is never going to change. The mass of the ball is not going to change randomly, so I could sort of erase this I if I wanted. Because it turns out that the mass of the bat and the ball at the beginning are the same as the mass of the bat and the ball at the end, so they only have one mass. We don't need to keep track, but the velocities do change. So this I and F are important. So what I want to find is the new velocity of the ball, which is this, the final velocity of the ball. First, I'm going to do this entirely symbolically because it is much easier to do it symbolically than it is to do it with numbers. So that means that I'm not going to be plugging in the numbers. I'm just going to keep track that I want this to be alone, and I'm going to make it alone. So the first step is to get rid of this, right? When you do algebra, you want to do PEMDAS in reverse, right? And the first thing I need to do is addition and subtraction. I need to get rid of that. So I see some addition here. I need to get rid of this, and I will do that by subtracting it. So I will subtract the final mass of the bat and final mass of the ball from both sides. And this is what I get. Maybe you notice that the final momentum of the bat, I decided to color in a light blue to make it distinct from the initial momentum of the bat. But basically, I subtracted this from both sides. And what I got was this equation on the bottom. So what I still need to do to get the velocity of the ball at the end alone is I need to divide. Because this is being multiplied by the mass of the ball, and I got to get rid of that. So what I do is I divide this whole side by the mass of the ball, and I divide this whole side by the mass of the ball. So my final answer, once I divide both sides by the mass of the ball, and then these two cancel. So this cancels with this. So this goes away. The final velocity of the ball is the initial momentum of the ball plus the initial momentum of the bat minus the final momentum of the bat divided by the mass of the ball. And once you have this, you can just plug in the numbers. But I'm going to plug in the numbers into here because this is probably what some of you are going to want to do. So I'll plug the numbers into here and then solve it numerically in a different way. But if you wanted to, I would do it symbolically. Get this formula for the thing you want to solve, and then plug in the numbers after so you don't get confused. But I'll go all the way back up and solve this numerically. And so I need to plug in numbers. I need the mass of the ball, which it tells me the baseball has a mass of 1 kilogram. So wherever I see the mass of the ball, I'm going to put 1 kilogram right there. And then also on the right side, the mass of the ball doesn't change. It's 1 kilogram. So its initial velocity is negative 20 meters per second. Oops, thought that was a highlighter still. So the initial velocity of the ball is negative 20 meters per second. That doesn't tell me anything about this, though. That doesn't tell me anything at all about this. So the batter swings an 8 kilogram bat. That's the mass of the bat. So 8 kilograms. And the mass doesn't change, so it's the same at the end. 8 kilograms at positive 25 meters per second. So this is how fast the bat is going before. So I'm going to say 25 meters per second. I could put the positive there, but multiplying by a positive number doesn't do anything weird like negative numbers do. So after the hit, the final velocity of the bat is positive 4 meters per second. So where it says final velocity, I'm going to put in 4 meters per second. And it wants me to find the new velocity of the ball. So I'm going to make that black. This is what I want to find, this velocity. So these are added, equals, and then added. So this is my equation. I got to solve it with algebra. So the first thing I'll do is negative 20 times 1. Well, that's negative 20. That's the momentum here. 8 times 25 is going to be 200. So this is the combined momentum at the beginning. That's equal to, well, 1 times v, that's just v, the velocity of the ball, plus 8 times 4, which is 32. So I have simplified it. The next step is negative 20 plus 200 is going to be 180. That's equal to the final velocity plus 32. So in order to get rid of this plus 32, I have to do minus 32. And what I get is that the velocity is 180 minus 32, which comes out to be 148 meters per second. I should have been keeping track of the units the whole time, but I got kind of lazy. It's equal to the velocity of the ball at the end. 148. That is the same number I would have gotten if I plugged it into the symbolic equation I got at the beginning. Maybe you thought this was easier. A lot of people do. If you think this is easier, just do it numerically. So other kinds of questions I can ask you are when two things stick together, or they carry things along with it. So this thing that we did at the beginning, where they bounce, these are called elastic collisions. And the reason why elastic collisions bounce is because in elastic collisions, the kinetic energy is conserved, which doesn't always happen. Energy is always conserved, but not always kinetic energy. When the kinetic energy is not conserved, you have an inelastic collision, or a not elastic collision. So in this case, where they stick together, it is also called a perfectly inelastic collision, because so an inelastic collision is when the kinetic energy is not perfectly conserved, but in a completely or perfectly inelastic collision, they totally stick together. They don't just sort of stick together. And that's what we'll be dealing with in this class because it's easy. Okay, so I'll write down my equation. This is the equation I got to use. Mass velocity initial plus mass velocity initial equals mass velocity final plus mass velocity final. So I know I'm going to use that. So a car with a mass of 1,500 kilograms and velocity of 40 meters per second runs into a stationary dumpster. That means the velocity is 0 with a mass of 1,000 kilograms. The car carries the dumpster along with it. So what is the final velocity of the combined mass? There are a couple ways you could think about this. The first thing I'm going to do is do this entirely symbolically. So in a completely or perfectly inelastic collision where they totally stick together, this is going to transform into a characteristic other equation. But I'll show you how I get there. So the key here is to realize that the blue mass is going to be the dumpster, the red mass is going to be the car, but at the end, they have the same final velocity because they're stuck together. If they're stuck together, they're going at the same speed. So this VF is going to be the same for both of them. So I'm going to put it in a different color to sort of symbolize that. The final velocity is going to be green now. So the final velocity is not going to be green because I don't know where my green pen is. It'll be orange. So they have different initial velocities. One of them is stationary. The other one is going at 40 meters per second. But they have the same final velocity because they're stuck together. You might not remember this, but in math, when you have something like 4 times x plus y, that's the same as 4x plus 4y. If you have the same thing multiplied by two numbers that are added together, you can sort of pull it out like you did here. These 4s, because they're on the x and the y, you can pull them out. So this case is very similar. We don't have a 4, we have a velocity that is combined by both of these. This velocity is the same, so we can pull it out. And what you get is this equation. You pull the velocity out because it's multiplied here and here. So you can do the same thing I did with that 4 just now. Keep in mind that this is the combined velocity, the red mass is the mass of the car, and the blue mass is the mass of the dumpster. So maybe I'll make that obvious. Like car, car, dumpster, dumpster, car, car, and this is both. A lot of the times we sort of rearrange this and we do mass of the car plus mass of the dumpster times the velocity just to make it seem more like the equation momentum is equal to mass times velocity. But these two are entirely equivalent and you can do whichever one you like better. So what I do in this case is I will use this equation, but I will use it in this form because when the two things stick together, you have, oh, this is the other way you could think about it. I almost forgot. So on this side, I have two things. So I have the momentum of the car, and I have the momentum of the dumpster. But on the right side, they sort of fuse and form into one thing. So I only have the momentum of the combined mass of stuff. So another way you could think of it is that you have two objects here, and they combine to form one object. And so the momentum of the mass is going to be the mass of the, oh man, maybe I shouldn't say mass, I'll say blob. So the momentum of the blob is the mass of the blob times the velocity of the blob. And the mass of the blob, well, it's made of the car, so you got the mass of the car, and it's made of the dumpster, so you got the mass of the dumpster. So the mass of the blob is this. So another way that you could get this equation right here is you could say, well, momentum of the car is mv car, the momentum of the dumpster is mv dumpster, and the momentum of the blob is the mass of the blob times the velocity of the blob, which is what we want to find. So the velocity of the blob. So there are two different ways to get exactly the same equation, but let's say that this is the equation we have. So I want to find out the mass of the car. Okay, so I'm going to do it numerically first this time. Mass of the car times the velocity of the car. So in this case, the mass of the car is 1500, the velocity is 40. So I have 1500 times 40. This is in kilograms, and then 40 meters per second. So I add together this momentum with the momentum of the dumpster, which is the mass times velocity of the dumpster. The dumpster is 1,000 kilograms, and it starts stationary, so it's not moving. So the mass of the dumpster is 1,000 kilograms times 0 meters per second, because it's not moving. That is equal to the combined mass, which is the mass of the car, plus the mass of the dumpster, in kilograms, obviously, times the velocity of the blob, which is what I want to find. So, plugging in the numbers, I do 1500 times 40, plus, well, this is 0, so it cancels, is equal to 1500 plus 1000, so that's 2500 times the velocity of the blob. So this, 1500 times 40, that's equal to 60,000. And the units for momentum are kilogram meters per second. That is equal to the mass of the blob, 2500 kilograms times the velocity I want to find. So what I do is I divide by 2,500 kilograms on both sides. So 2,500 kilograms. And what that gives me is 60,000 divided by 2,500. And 60,000 divided by 2,500 is 24. The units for momentum are kilogram meters per second, but we're doing velocity, right? So the units for velocity are meters per second. And you could even figure that out here, right? You have kilogram meters per second divided by kilogram, so this kilogram cancels with that kilogram, and you only get meters per second at the end. Anyway, so this is your answer. The key with inelastic collisions is that you have this form of equation, where you have two things on the left and one on the right. The last kind of thing I can give you, the last kind of thing you can deal with, the last kind of question I can give you are explosion questions, where you have a stationary 500 kilogram cannon holding a 5 kilogram cannonball, sitting on top of a castle, and then after it fires, the cannonball is moving forward. What's the velocity of the cannon backwards? So to do this one, you do the same thing. You have the mass of the cannon, velocity of the cannon at the beginning, plus the mass of the cannonball times the velocity of the cannonball at the beginning is equal to the mass of the cannon plus the velocity of the cannon, or times the velocity of the cannon. What am I doing? At the end, plus the mass of the cannonball, velocity of the cannonball at the end. So in this case, this is 0, the velocity of the cannon, because it's stationary, so that goes away. The velocity of the cannonball is also 0 at the beginning, so this goes away. And what you get is that 0 is equal to the mass of the cannon, velocity of the cannon, plus the mass of the cannonball, velocity of the cannonball. This is the initial side, and this is the final side. So if you want to figure out the velocity of the cannon at the end, which is this right here, I want to figure out the velocity of the cannon at the end. The first thing I do is I subtract the mass of the cannonball, velocity of the cannonball from both sides, so I subtract this, and I get minus mass of the cannonball, velocity of the cannonball, is equal to the mass of the cannon times velocity of the cannon. And then after you do that, well, you want the velocity, so you got to get rid of the mass, so you divide it. So divide by the mass of the cannon. That goes away. Divide by the mass of the cannon. And what you get is that the velocity of the cannon at the end is -1 times the mass of the cannonball, velocity of the cannonball, over the mass of the cannon. So in this case, the mass of the cannonball is 5, the velocity is 100, so this top is going to be -500 divided by the mass of the cannon, which happens to be 500 kilograms. So you divide -500 by 500, and you figure out that the cannon is going at 1 meter per second backwards. That's what the negative means. So these are all different versions of the same thing. This one equation will tell you how to do all of them if you use it creatively. You use it straightforward in elastic collisions, you just plug in the numbers and solve. For inelastic collisions, you have to get it into this form first, where you have two things on the left and one on the right. And you can do that because the shared velocity is, it sort of distributes out. And then for explosion problems, you are always going to end up with something like this. The positive momentum of one object, so object 1, is equal to the negative momentum of object 2. Because you're always going to have 0 at the beginning, because that's what an explosion is, they're not moving, and then you have these two things at the end. And the only way that you can get this to solve is if you subtract one of them from both sides, and it becomes negative. Anyway, I hope that was helpful.